Hey guys, so in this video I'm going to go over some of the topics that a lot of us seem to struggle with on the mid-unit test that we took, and then after watching this video and going through it, you'll be able to retake the test if you would like. So one question that we seem to struggle with, a lot of us seem to struggle with, was the question about the can of soda at room temperature, and then you open it up and there's a hiss, and then it's asking you what has changed inside of the can of soda. So let's look. Let's say this is our can of soda right here, right? And so it's not full of liquid, it's almost full. Maybe the liquid's up to like right here. And then there's carbon dioxide, there's gas, little gas molecules, up in here. And so there's a fairly high pressure inside of there when it's closed. And you know that because when you open it up, you hear the hissing sound. And then, so what's actually going on when you open up the can? Now, what's happening is when you open the can here, you make a hole in here, and there's gas molecules, and they're running into the sides of the can. That's what pressure is, right? It's the force of the gas molecules or gas atoms hitting the sides. And so when you open this up, when you create a hole right here, the gas molecules can rush out now, right? Because there's a higher pressure inside the can, there's a lower pressure outside the can, and just like diffusion, gas molecules go from area of high pressure to low pressure, just like diffusion and concentration. From high concentration to low concentration, they go from high pressure to low pressure, and so they rush out. And so that hiss of air is the gas escaping from the can. And so that's what's changing inside the container, the amount of gas, right? There's a lot of gas in here, you open it up, some of it rushes out, and so the amount of gas is changing. The tricky part was it said atmospheric pressure, and the atmospheric pressure just means the pressure all around us in our world, the pressure of the atmosphere of Earth, right? And so that pretty much stays the same. It's you opening your can of soda is not going to change the atmospheric pressure at all. So it's the amount of gas inside the container, not the atmospheric pressure, that's changing. Then another question that was kind of difficult for us was another diffusion question. This one was about actual diffusion. Then it says there was basically this thing, there was like a spout, you can think of it, whatever you can think of it, and there's gas coming out of this opening here. So there's gas coming out of this opening, and then it's asking you which sensor will detect the highest concentration of this gas that's coming out, and you get different distances. And so the thing to know about diffusion and about gases is that the concentration will be highest closest to the source. So if our source is right here, where I'm drawing this yellow circle, this is our source, and the concentration is going to be highest right at that source. And then it's going to be, so if we have maybe different distances, like right here, 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 and here, and this is distance, let's label it distance A, B, C, and D, the highest concentration of gas is going to be at A. Highest concentration because it's closest to the source, right? And then the lowest concentration, of course, is going to be at D. Lowest I'm abbreviating concentration there. Right, and so you're just looking for the distance that's closest to the smallest distance from the source, right here, from the source to A. The source is where the gas is coming out, like the spigot or the spout. So A will have the highest concentration. And then one last thing, it shouldn't matter if it's in front or behind, right? Because gas is coming out and it's spreading evenly in all directions, right? So if we had another thing behind the source, and this was labeled A because it's the same distance as this other A, if those are the same distance, both of those A's from the source, they'll have the same concentration. So it doesn't matter if it's in front or behind, just whatever's closest to the source. Okay, a couple questions we had was identifying a gas law based on its assumptions. And so make sure that you know the assumptions for all the gas laws, for Boyle's law, Charles' law, and Gay-Lussac's law. And so I think we did pretty good, it looks like, on knowing the actual law. We just have to remember that the assumption, what's held constant. So when we're talking about the assumptions of a gas law, basically it's asking what is held constant in that gas law. And so I'll do an example here. If we're looking at Boyle's law, right, Boyle's law. Boyle's law is P1 V1 equals P2 V2. And then the assumptions of Boyle's law, remember the assumptions are always for all three that there's a fixed amount of gas. So that's for all three. And then we know for Boyle's law that there's a fixed temperature. Because remember with gas laws, there's three variables that we're looking at. We're looking at temperature, volume, and pressure. And so each gas law has two of those variables. So Boyle's law has pressure and volume, and whichever variable of those three is not in the specific gas law, then that's what we hold constant. So fixed or constant means the same thing. So a constant temperature or a fixed temperature. And then all three have this one. All three have the fixed amount of gas. So if you're given the assumptions or what's fixed about the gas law, you should be able to figure out which gas law they're talking about, because you can write down the three gas laws and say, oh, okay, well, it's asking me for this says it has a fixed temperature. Boyle's law does not have temperature in the equation, so they must be talking about Boyle's law. Okay, last thing I want to go over is actually a question related to Boyle's law. It's about a balloon in a closed container, and this one is a little bit confusing one, so I'll draw a picture here. So here's our container, and then it says there's a balloon inside of it. And remember, here's our little string on the balloon, that this container is a closed container, so no air can come in or out of this. It's like an airlock kind of. No air can come in or out. And so then it says you do something to the pressure in the container, and it's asking you what happens to the balloon. So if you think about this, if you draw yourself a picture and you think about this, if we have this container, and then let's say we have the pressure in the container. Let's say we have the pressure in the container, or let's say we double it. Actually, let's say we double it. So we put more air into this container. We double the pressure outside the balloon. Now this is important. It's saying you double the pressure in the container, not inside the balloon. So this pressure in the container is doubling, so it's pushing in more on the outside of the balloon. And if you think about this, right, if you squeeze, it's like squeezing the balloon. If you squeeze a balloon, what happens to it? Well, it gets smaller. And they are inversely proportional. This is Boyle's law. Remember, we're dealing with pressure and volume. Pressure outside, the volume of the balloon. So they're inversely proportional, meaning that if you double the pressure outside the balloon, you'll have the size of the actual balloon. Same thing if we did it the other way. If we halved the pressure, if we had less pressure in here now, if we took air out, there's less pressure, there's less force pushing on the balloon's going to get bigger, and so if we have the pressure, then the volume of the balloon will double. Alright guys, I hope that helped. Good luck on the retake.